Thank you. It's such a great pleasure to be here to talk to programmers, developers. Thanks very much for the organizers to have me here. Thank you all for being here as well. So I want to talk about the future of programming. What do we expect in programming languages? Well, what I'm going to talk about here is the future is a little blurry because we have some of these already, but I want to talk a little bit about what we can see, what we can expect as well. I love programming. I love programming languages. And today, I program in about maybe 15 different programming languages. What I'm telling you in so many words is I'm not good at any one of them. But I love programming, and every day I have to write code. But one of the things I enjoy today is not just writing code, but also to rewriting code, refactoring it. And I care deeply about how code can be really expressive and how it can be written to maintain. So we've come a long way, but people often tell me that things change really fast in our field. And this is common. You talk to any programmer, and they would say, oh my gosh, everything is changing all the time. And yes, there is some truth to it, but at the same time, we have to wonder, where did we come from, where are we going? Well, I remember, as a very young programmer, spending my days on VT100 terminals. It was a lot of fun writing code on those machines where you only had the terminal in front of you, not the real processor. And then, of course, we had personal computers, we had laptops, and all of a sudden, now we are doing everything on the cloud. And I'm like thinking, gosh, I'm doing something what I did 30 years ago. And it seems to be a repeat. The history repeats itself. And of course, we've gone through all these generations. But today, we carry multiple core processors with us in our pockets. It's amazing the power of computing we have that we can carry with us every single day. But this reminds me of one experience I had. How do you explain to people? Today I work with people who are very young compared to, how old I am. And, but one of them is, seeing my children grow up to become, people in the field. But this was a few years ago. We were visiting the store, and my wife and I were with my son, and she said, oh, there's the whiteout. And looked at it, like, yeah, that's kind of awesome. And my son was very curious, and he said, what is that for? And I said, and my wife said, that's when people type on a typewriter. If you make a mistake, you use that to white it out and then retype on it. I mean, I should have kept quiet. But I was so excited when she said that I said, did you know that Daddy wrote his, a college thesis on a typewriter, but Daddy didn't know how to type, so your grandma typed the entire thesis for your dad. And my son kind of listened to it very patiently and said, what's a typewriter? This is when you kind of should know to quit the conversation, but I didn't. I said, typewriter, it's what you type on so that's a machine, and I kind of talk about what a typewriter is. And then he's very patient, listens to me and says, and why would people do that? Why can't people just type on a computer and print it? And then I was trying to tell him that there was no computers and no printers back then when I was a child. And the more I say, he's kind of like, were you Stone Age when you were a child? He was thinking. And then, of course, as soon as we got home, I ran into my closet, and I decided to hide all my floppy disk. What would he think if he ever discovers that I had a bunch of floppy disks that I was using back in time? And then you realize that we lived through maybe 40, 50 years, and we see technology come to life, and then they just disappear. And the only place where you can see them is in museums. It's just amazing how the world around us keeps changing. But a lot of things have changed in the past 50 years. And I'm pretty thrilled to have survived this long. Last year, I completed my 50 years of age. And I said, to celebrate my 50 years, people do crazy things when they turn 50. And I blogged about it and said, hey, I'm turning 50, I want to speak in 50 user groups. This was a really bad idea. And the next thing you know, I was traveling around the world and speaking in 50 user groups. By the time I was done, I spoke in 53 Java user groups. But I couldn't have asked for better at all, because the 50th one literally was on top of the Eiffel Tower. The Java user group in Paris decided to hold it there. But in 50 years, I've also seen various different technologies come to life and die, and that's just pretty amazing. But when you look at computers, I have a good friend of mine. I'm old, but I've had older friends as well. And she was telling me back then, we used to have these huge mainframe machines, and these will fill up rooms like this. And they were really good at generating a lot of heat. That's what they did. And then, of course, if you think about it, what did people do with these machines? They did wonderful things. They discovered, they did science, they did astronomy and all that. But today we have machines which are even bigger than this, unbelievable. And then I notice what people do with it. I go to airports, and I've finally figured out I've nailed it. And this is what my analysis is. I admire the human quest to create new powerful devices and technology. So humans have options like never before to play solitaire. That's what people do. And I'm thinking, oh my goodness, with all this computing power, all we do is we play solitaire. That's what we do, right? But anyway, there's at least some use for it. Well, but when you look at these technologies, how are we programming in the modern century? How are we programming in the modern age? I'll tell you how I've seen programmers program today. So here's what they do. They sit down and they say, for int I equal to 0. Is that like really? And is this what we're going to be doing? And in fact, this is a bit of a shame. When I was a young programmer, my wife and I, she would watch me program, and I was programming predominantly back in time in C++. This happened a few months ago. I was sitting and writing code at my desk, and then she came along to get something, and then she looked at me and said, oh, Venkat, shame on you, you're still writing C++ code. And I looked at her and said, I protest, this is not C++. Come take a closer look at it. This is Java code I'm writing. And then she said, And then she kind of looked at it and said, okay, I'll give it to you. You don't have a free and a delete in there, but it's C++ for every practical reason. Come on, give me a break. And I felt a little ashamed that she was actually making that observation, but to a great extent, if you notice, the code is not very different from what I wrote 30 years ago. And that is something to really think about in terms of, are we really going to continue program in the same old way in terms of how we program with that? And then that is a bit shocking because while a lot of things have changed, a lot of things have not changed. And some things are so fundamental to what we do. This is exactly the fundamentals of our field. For example, we talk about Turing completeness when it comes to programming languages. And we define what a Turing completeness is when it comes to languages and what we expect from them. And of course, we also take care of the fundamental bottleneck. And how do we deal with it? And systems suffer through some of those architectural constraints. But having said that, though, let's think about this for a minute. Does anyone remember the year object-oriented programming was introduced? Throw a number at me. Don't worry about being wrong. 1960s, I heard. Actually, it was 1967. Now, think about that for a minute. That was year 1967 is when these two gentlemen, Dahl and Nygaard, introduced this idea of object-oriented programming. They didn't coin the term object-oriented programming, but they pretty much did everything else. Alan Kay eventually coined it as object-oriented programming. So this was the language Simula they had created, and they had created this idea of object-oriented programming where you can model this data and behavior and all those good stuff. Does anyone remember the year when object-oriented programming became mainstream, like everybody started coding it without even thinking about it? I'll give you a clue, it's after 1967. How about 1990, give or take, right? Give or take 1990. Now think about that for a minute. What was introduced in 1967 became prominent in 1990. What is that? A good 23 years, isn't it? If OOP was a human, it had a terrible neglected childhood, and nobody wanted to hang out with it. But when it turned 23, hey, handsome, do you want to hang out together? And everybody was eager to use this. That was a 23 years. Why does it take 23 years for something to become prominent? Let's think about it. Well, what year do you remember was functional programming? Or even better, what year was lambda calculus introduced? Anyone remembers that? I hear 1955. Well, everyone knows Alan Turing, knows of Alan Turing. Well, this was Alan Turing's professor, Alonzo Church, who introduced in 1930s. In 1930s, we had lambda calculus get introduced. One last question. What year did functional programming become mainstream? Okay, that was a trick question. Not yet. And a good 90 years later, we are just warming up. And we are like, oh, this seems like a great idea. So when people tell me things change really fast, I always ask them, what are you smoking? Because if 25 to 30 years to 90 years is the speed of change, I don't think that's what the word speed really means. So on one angle, we are getting new framework and new libraries every few months. Okay, I'm sorry, I didn't think of JavaScript when I said that, every few minutes. But at the same time, though, adapting to a different paradigm takes a very long time, takes a long effort. And I kind of wonder, why is that taking so much long? What is the reason for it? Well, the reason why it takes so long to adopt really is, why 20 years? Why 30 years? Why 50 years? And here's a beautiful quote by George Santayana. He said, "Those who cannot remember the past are condemned to repeat it." And that is one of the reasons why we need to really spend some time asking the question, why do things take so long? What were things? And so we can know where we are heading. And programmers, unfortunately, don't adapt too well. This has been my observation and experience over the years. Programmers are quick to learn a new library, but they're not really as willing and open and eager to adapt a new paradigm or a new language for that matter. And that takes a lot more effort. And you kind of wonder, why is that happening? Why does it take so much time? And part of the reason is we often take change in bite size. Now think about this for a minute. Why does the for loop in Java look like the way it looks? Oh, very simple. Because the for loop in Java looks exactly like the for loop in C++. Why did the for loop in C++ look the way it did? It's because that's the way the for loop looked in C. Why did the for loop look like that in C? I mean, you keep going back and you realize that they're clinging on to what people were used to. And we are able to just make bite-sized improvements, but we cannot drastically change what we do. It's really incredibly hard for us to do that. And this really brings back to the question, habits are really hard to change. It actually takes a new generation. And this is something we forget. It actually takes a new generation. What is 20 years? What is 30 years? And honestly, that's a new generation. And I'm quite happy to say that. This reminds me of an experience. I was in a conference a few years ago, and I had just finished a keynote, and I got down and I sat down in my chair, and there was a young lady sitting next to me, and then she said, "Oh, that was a great keynote. Thanks for coming and speaking." I said, "Absolutely, thanks for coming." And then she said, "Well, I went through a master's program, and I graduated 2 years ago. I've been working in the industry for 2 years. You know, when a lady says she's done a master's degree and she's been working for 2 years, you kind of can guess how old she is." And then she said, "Can I ask you a personal question?" I said, No, lady, we don't do personal questions. Thanks for coming to the conference. We are done." And she said, No, I really want to ask you this one. Please allow me to ask this one personal question because I'm very curious about you. I got to know this." I said, "Okay, I'll give you one question. What is it?" And she said, "Can you tell me what year you graduated from college?" I said, No, we're not doing this." And she said, No, please tell me what year you graduated from college. I said, "Okay, fine." And I told her the year I graduated. Her face just blossoms right away and says, "Really? That's the year I was born." And I looked at her and said, "Can you do me a favor?" And she said, "What can I do for you?" I said, "Can you reach over and get my cane for me? I need some help walking." And all of a sudden, I felt like this old guy sitting next to this grandchild of mine, in a way. And that evening, I went back to my hotel. I was thinking about this experience. And I said to myself, this is amazing. Because I am here working shoulder to shoulder, so to speak, with a colleague of mine who was not even born when I finished my school, when I finished my college. And what that tells me is there is new thought and new ideas. And they always, like my children, ask the question, why? Why are you doing this? Why are you doing it? And then I realized change doesn't come from people who cling on to ideas. Change comes from people who question those ideas. And then they say, why are you doing this? Why can't we try something else? And they have that new energy. And as time goes on, that very lady I talked about is going to be old as me. And she will have to have her turn to work with the next generation. And then I realized something absolutely phenomenal. The change happens because as time goes on, something beautiful happens. Guys like me just disappear in the sunset. We've done our part, and there's this young generation coming up. And then I realized something very profound that day, that nature comes with a built-in automatic garbage collector. This is just amazing to me. And that is absolutely rewarding in my mind, because how terrible would it be if people like me had to cling on to things forever. And the fact that there's a young generation that's coming and questioning, and when I look at my children, that is what I love about it. Because yes, they are naive to a certain extent, but they have that new energy and say, why are we doing it this way? Why can't we do it? And by giving them a chance to do it, sometimes they realize they were not right, but other times they do have better ideas, and we can innovate and we can find better ways to do. But we are poised for a very big change moving forward. And it all started back in 2003 to 2006 timeframe, where we saw two different things come about. One is the change in hardware. And we figured out we cannot put more things on a processor because we had to really deal with heat dissipation. We couldn't just do it. So we started going towards a multi-core processors. So the hardware changed around us. Second, the business changed around us. People started doing different things with the technologies and the hardware available. And all of a sudden, the programmers looked around and said, gosh, what do we do to support this? On one hand, this is being squished from both ends, isn't it? The hardware is changing, and the business demand is changing, and we are stuck right in the middle as programmers. We better start doing something different. And there's a cry for help in that regard. And things like the modern demands, cloud computing, big data, microservices, IoT, machine learning, AI, a lot of these things are coming our way, not to mention NoSQL or MapReduce algorithms and reactive systems and so on. But if you really think about it, this is very frustrating. The web applications we develop, and don't get me wrong, we're doing beautiful work, we're producing results, but just think of the web for a minute. How are we building the web today as we speak? Call it Web 2.0, whatever you want. But at the end of the day, what are we really doing? Well, the old web simply, unfortunately, is this, isn't it? It's stateless request and response protocol. Now, what does this really mean to be stateless request response protocol? Well, you are sending a request to a server, and it sends back some kind of a response. It could be XML, could be HTML, could be JSON, doesn't really matter. But at the end of the day, what does this really mean? You make a request, you get a response. You make a request, you get a response. Now, what that means is that when you make a request and get a response, you are pretty much, it's a stateless request and response. Now, how does this feel to be programming the web like this? So here's an example of, I'll tell you how it feels for me to program the web. So imagine for a minute, I saw you yesterday evening, and you are running out of the building, and I ask you, hey, where are you heading? And you say, oh, I'm going to go catch this movie. I've been waiting to watch this for a long time. Okay, have a good time. And I see you this morning, and I ask you, hey, did you go to the movie yesterday? You say, oh, yes, I did. And I say, how was it? And your response is, how was what? That's how we program the web today, isn't it? Because, if you ask me, how does it feel to program the web? It feels like you are programming with Dory from Finding Nemo. Because hey, I'm Dory, how are you doing? And every few minutes, you have to reintroduce yourselves. There's no context to maintain. And that is really sad. And that's not something we want to build infrastructures with. What I would like for the new web really is to move in a different direction altogether. And this is one thing I'm absolutely thrilled about, is continuations. And we are not too far from this. Continuations has been around for a long time, but finally, we can use continuations in mainstream languages. Like what? Let me give you an example of continuation and how it feels like when we can use it. So here's an example. I'm going to give you an example in JavaScript. I know that's a bit scary, but I think we can learn from everything in this world. So let's give it a try. I'm going to write a function right here. We'll call it foo for lack of better words. And what do we want to do? I want to say for constant value or element is good enough of, and in this case, let's call foo right now. So all I'm going to do is basically loop through this and get the value out of this. But how does this work in this particular context? So I'm going to print out in the loop for a minute. But for me to use that foo, it's got to generate some values for me. So I'm going to go over here and say in foo, or we'll call it entering for a minute. And I'm going to just enter this, but I'm going to yield a value of 1, let's say. Let's just start with this. So for this purpose, I'm going to mark it with an asterisk. That becomes a generator. But if you notice, it says entering in the loop. And I'm going to simply say over here, how about this? We'll say in the loop with. And I'm going to just print out the value of e so we can display it. And it says in the loop with 1, as you can see from the output. But what is really cool about this is, when I run this, I can come back here into this code. I can do something like this. Let's go ahead and say step 2. And I'm going to yield at this point 2. And you can see from the output how we are having this conversational state. So this brings us to an idea of coroutines. So what's a coroutine? Well, a subroutine is where you enter, you execute, and you exit, and everything is forgotten after it. A coroutine is, on the other hand, you leave from here. But imagine for a minute, when you leave from here on this line, imagine I return a tuple, where a tuple contains a result of the call, but the second part of the tuple captures the remainder of the code state. And so when you fire back into that, you can come back and execute where you left off. So all of a sudden, you have a function in front of you, but you enter the function, you exit away, but you re-enter where you left, you execute some more, and you leave, and all of a sudden, you and I have a conversational state. For example, hey, did you go to the movie yesterday? I did. How was it? I loved it. Did you go with any friends? Now notice how we are building on this conversation. You and I could even meet after a few weeks, and we can pick up where we left because we can come back to that conversational state we left with each other. What if we can start programming like this moving in the future? Like, for example, this, of course, we know is Java. And if you ask me where I'm putting my money, I'm putting my money into one thing. I'll bet here on the stage today. In 5 years from now, Java will be the best asynchronous programming language in the world because they've completely realized that asynchrony is far more important than parallelism. Don't get me wrong, I love parallel programming. My dissertation was in parallel programming, but that doesn't mean that's the right choice for everything we do. Asynchrony is extremely important. So here's something we could do potentially. I can say, for example, scope is equal to new, and we will go ahead and say continuation scope right here. Let's just create a scope for just a minute. So this is just a continuation scope I'm creating here in Java. Then what am I going to do? I'm going to say over here a continuation, we'll call it continuation, is equal to new continuation. We'll pass the scope to it. But let's go ahead and just say do work, just a function I want to call as do work. So what does this function do work really do? Let's basically say here public static void do work, and within the do work, all I'm going to do here simply say is entering. Hey, I'm writing code in Java, much like I've written code in JavaScript a few minutes ago. But then what I want to do here is to simply say while, and in this case, let's say while not of the continuation dot is done. And what do I want to do at this point? I'm going to simply output over here in the loop, just like I did in the Java side. But then I'm going to say over here, let's say continuation.run and call that little continuation. And when I do this, what am I going to achieve out of this goal? Let's go ahead and import java.lang over here .continuation.star as a static scope right here. But then what I can do here is come into this code, and I can do a yield just like I did on the Java side, JavaScript side rather. And then I can simply say output step 2, which is the step I want to continue forward, and I'm going to yield the scope right in here one more time. Now, clearly in this case, we have a do work, and I've implemented a coroutine, so to say, where you can enter right here, do some work and yield a result back, and then do some more work when you're called upon, and you can continue further. And within this code, of course, until I'm done, I'm going to keep calling the run method on it. So when I execute this code, what does that do really? Where's the scope coming from? Well, the scope is going to come from the continuation scope. So let's go in here and say continuation scope, and let's bring it as the scope right in here. So when I execute this code, what it is going to provide for us is the ability for us, let's actually make sure this is working properly. So here's the do work method I'm going to call into this and pass the continuation with the scope itself. Let's see what the error is, and we'll resolve it and move forward. So where's the yield coming from? So the yield is going, did I spell yield correctly? It does require you to spell it correctly, unfortunately. Okay, so let's try this again. So that's going to be yield. Hey, at least I'm consistent in misspelling it. You should give me the credit for that. Okay, so let's go ahead and run that code again and see what it does. So this is going to bring in the continuation. Okay, do work is in class sample cannot be applied to this kind of type, Why is that? Because I didn't pass the scope to this guy, so let's go ahead and pass the scope right in here. So let's go ahead and try that one more time. And when you execute the code, you are getting exactly the same behavior as you did on the JavaScript side, but this is within Java. This is an example of continuations in Java. This is not in production, of course. We will have this within the next 3 to 5 years, hopefully. But the point really is, this is Project Loom, and I just did a build of Project Loom on my machine. I'm not suggesting you would use continuations like this. Continuations will play a role behind the scenes, but this is just to give you an idea about how what I showed you in JavaScript is something we could potentially do in Java. And we can have these kinds of functions where we can call into something and have a conversational state into it, and I can tell you I'm absolutely thrilled about where we are going with this. So if you ask me if there's one technology I'm absolutely excited about in Java, that is going to be continuations and fibers and Project Loom. So this is something that I'm really looking forward because it's got the potential to fundamentally change the way that we do application development moving forward. And especially web development, I'm hoping is going to fundamentally change based on these ideas. And you can save the execution state and return to that point and execute further, and I think that is extremely powerful. So languages should make simple things simple and hard things manageable. So what are the things I really want in programming languages? Well, the few things I want is languages must promote higher level of abstraction. And that is because we as programmers can focus our efforts on the application rather than with the infrastructure and the code and get dragged into the complexities of things. I want languages to provide composability, and the language should be supporting really good declarative style. But the very first thing I want is, I want languages to be expressive. Now, this is one area where I think we are very lacking in Java. Because in the case of Java, we are forced to write a lot of code to do simple things. And Java is definitely moving in this direction. I'm beginning to see this change starting in Java 12, for example. Some library of functions introduced in Java 12 can remove 15, 20, 30 lines of code by giving us functions that can get things done easily. Java is going to introduce ability to do smart casting in the future. Java 12 has introduced the first version of change towards pattern matching. And that's going to remove so much verbosity in our code. But if you really think about it, what does expressiveness mean in that context? Well, here are a few things I want to think about. Suppose I have fruits with me. And if I have the fruits and say list of, let's say, apple, and let's say we have banana. So I have a list of fruits with me, and I'm going to just print it. I'm going to say fruit right here, and I'm going to print it. So when I do this, you can see apple and banana. This is Kotlin code where I'm just printing those two objects. But I want to add to my fruit. What do I want to add? I want to add to the fruit orange. So what do we do in Java? You want to add. But wait a minute, the word add simply means I should be able to do this, isn't it? So why can't I just use a plus and do an orange? It requires me to spell things properly, but nevertheless. So if I were to do this, how does this work? Why can't... Okay, I give up. So the point really is that you can see how I can just add it. And maybe that's the name of a new fruit, who knows? So the point really is that you can perform additions to it. The list is immutable, all right. You're not mutating the list, but you're able to create a new list with adding it. And how it becomes expressive when languages can provide this for you. Or here's another way to think about it. What if I have, let's say, names is equal to, let's say over here we have Jack and Jill. So I want to be able to print Jack and Jill. This is JavaScript in this case, but I want to print Jack and Jill. How do I do it? I can say constant name of names. And what if I can simply print the name out like that? So in this particular case, you can simply loop through the names given to you. This is JavaScript. So given the names, you're able to just print it. But what if I want the index to be printed as well? And the concept of destructuring. So what if I say, give me the name and the index, and I can get that from the entries over here. And then once I get that through the entries, I can then, of course, ask it to get me the values, and I can simply go ahead and print it. Well, again, talking about expressiveness, Java is going to have raw strings sooner than later. And what we can do is be able to use some of these capabilities, and the code becomes a lot more expressive and concise. What if languages can consistently start providing these features? Our work gets really done easily, and that's exactly what I want from the expressiveness point of view. And I want composability. And to a great extent, I would argue Java 8 gives us this. Composability is where we can compose a series of operations. And there are two places where you can enjoy composability in the case of Java. And we all know we can do something like this. We can say if I have names is equal to, let's say, list of some names over here. And what I can do in Java is I can say names.stream, and I can beautifully compose. I can say filter, given a name.length, for example, is equal to 4. And then I can map this further and say a string to uppercase. And then, of course, I can say for each and print out system.out and print line, and I can print these values out. So you can do this beautiful composability in Java already, and we know that we can exploit some of those capabilities nicely in the case of Java. So this is going to be a very powerful way for us to write code in Java, as we know. But to me, what is really exciting about this is not just the ability to compose these operations. One of the core capabilities in programming languages is, I'm going to save this away, I'll come back to this in a minute. So one of the core capabilities is something along these lines. So what if I were to bring in a function.star? And I have a function here, let's say integer comma integer. We'll call it increment is equal to, given an element, give me an element plus 1. So surely I can say increment apply, and to this apply I can send a value of 5. 5 incremented becomes a value of 6, and that's exactly what I want to see as an output. But what if I were to create one more thing? We'll call it as doubled. And doubled is going to take the value and times it 2. And I can, of course, come back here and say output double.apply, and I want to double the value of 5. 5 times 2 is 10, as we know. But what if I want to compose both of those together? And Java gives you this, sure, but I want to see this in a much more natural way if we can. So what if I can say increment and then doubled? And I can simply create and then apply on that one a 5. I increment 5, that becomes 6. 6 is doubled to 12, and the result I'm expecting to be a 12 at the very end of this. So you can compose functions to form bigger functions, and that kind of composability is extremely important for us to be able to build upon abstractions. So what that means is, not only can you do object decomposition, you can do functional decomposition as well. Functional programming languages provide this, but any language that wants to provide support for lambdas and functions should be able to provide this very naturally as well. So we need to be able to compose things very effectively. Well, in addition to the composability, what I want languages to provide is efficiency. Now, efficiency is extremely important. Why? Why is that? Because going back to the code we saw a few minutes ago, if you look at this code we wrote, now obvious question is, what is the performance of this code? Now, in this case, suppose I want the first one, if I say find first over here, and if I ask for the very first element to be given, and if I output this, you can see from the output, it is actually an optional of Dory that you got, which is the first one. But it would be really sad if this code went on to process every single element in this collection. And that is one of the reasons why you don't want just code that looks beautiful and cute. And this is something I want to emphasize. A code that is cute is not sustainable. Because when a code is cute, you're going to look at it and say, oh, that's cute. And within 5 seconds, somebody says, but what's the performance? And you're like, oh, it's going to be slow. Get out of here. Nobody's going to be interested in cute code that doesn't perform really well. And so from that point of view, when you look at this code for a minute, if I take this code for transform and say name, and I'm going to call a function called transform and pass the name to it. So what does the transform function do? All I'm going to do is public static, let's say string transform, takes a string name, and all it's going to do is return name dot to uppercase, let's say. But in this case, I'm going to output called with, let's say, plus name. So the beauty of this code is, when I execute this code, it is going to call the transform for Dory, but it never touches Gil or Bruce or Nemo or Darla for that matter. And what is that? What is the reason for that? That is because of lazy evaluation. So I'm going to emphasize, expressive is important, but not sufficient. And that is something you need to really keep in mind when it comes to designing the systems. So I'm going to simply throw out this and say, cuteness is not sustainable. This is unfortunate, but true. This is one thing I always do. When a friend of ours calls and says, we have a new baby, my wife and I go to see the baby. And the first thing you will see my wife do is, how cute. And I always go to the child and say, child, this is not going to sustain, right? Because in human life, cuteness lasts for 2 years. The minute the child begins to talk, they say, you talk too much, be quiet now. And so you have to really produce results after a while, just cannot be cute and get away with it. So cuteness is not sustainable. Performance is absolutely important. And of course, that comes from lazy evaluation, and languages have to support laziness when it comes to this, because laziness really comes down to laziness is equal to efficiency. So this is extremely important in terms of what we can provide. That is critical. But in addition to being efficient, I want languages to also keep in mind almost seamless synchronization. Almost seamless. I don't want it to be entirely seamless. And I want to emphasize this here with this particular example. Now, some of you may know this. In the very early stages of Java 8, this was like nearly 2 years before Java 8 was released, I was writing my book on Java 8 alongside Java 8 was being developed because I got drawn into it. But I remember the early days of Java 8, the functions like filter and map, all those functions were actually available directly on the list. You could write code like this back in time in Java 8, about 2 years before Java 8 was released. And when you looked at this, what happened here was you were literally able to call filter on a list directly. And one morning I wake up and I realized that they introduced a stream. And all these methods like filter and map were gone from the list. I was in a state of a panic. It's like, where did all these methods go? And then I found this new thing called stream, and I was a little surprised, like, why did they do this? But then I sat down and think about it and said, this is brilliant. And the reason this is brilliant is there is one very fundamental difference in the way things are done. And that is, if you think about filter, map versus find first, there's one fundamental difference. Filter and map are intermediate operations. Their evaluations is lazy. On the other hand, find first and methods like that are terminal methods. Now imagine they had introduced filter and map on listed directly. All of a sudden, you and I as Java programmers will look at a piece of code and say, I don't have a clue right now. Is this a eager evaluation or is this a lazy evaluation? And the point really is, the beauty of the word stream is the word stream gives you that little seam. So when I look at the word stream, it alerts me saying, so what does stream mean? To me, word stream means a semantical difference. And the key is, there's a semantical difference in the way the code behaves at this point. And the minute I see the word stream, immediately my mind says, aha, there's a lazy evaluation here, be careful. You are crossing a semantical boundary. This is no longer your territory that you are used to. The evaluation is very different. That visual hint is extremely important. If they had not given the stream, the code would have behaved in a way that is surprising. And the worst thing, as a programmer, honestly, what is the one thing you hate the most? It's a surprise, isn't it? And you look at this and say, gosh, I did not realize the code is doing this. So I want this to be, almost seamless. Like what? I'll give you an example here just to illustrate this point. I'm going to say over here, a fun task 1, and here I'm going to output entering task 1. And I'm going to output entering task 2. This is Kotlin code right in here. And then I'm going to create a task 2 as well. And the task 2 says entering task 2 and exiting task 2 as well, as you can see right in here. But then what I want to do is bring in the Kotlin coroutines. So I'm going to say import over here Kotlin x.coroutines. So, and then of course, let's go ahead and try calling this method right in here. So I'm going to say run blocking. I want to wait for this coroutine to finish. And I'm going to call task 1 right in here, call task 2 right in here. I'm going to simply say here, making the calls. Let's say making the calls. So when I run this code, what it's going to provide for us is simply that sequence, a very simple sequence, nothing really exciting, what you would absolutely expect from this call. But what I want to do, though, is I want to introduce an asynchronous operation, say launch over here. And I'm going to start this and say, go execute this off and launch it. So I'm asking it to launch at this point and say, go away and do it. But at this point, I'm saying, all right, that's great, but I really want to interleave these calls so I can perform operations concurrently. And for that purpose, I'm going to say yield over here, and then I'm going to go back to this code and say yield as well. But immediately Kotlin says, wait a minute, you are crossing a semantical boundary here, and you're going to get hurt by doing this. Because when you look at the code, you better know what you're doing. So this code will not work. What is the reason for that? Well, the reason for that is it wants us to really indicate that this method could be non-blocking call. So how do you specify that? But don't get me wrong, I love Kotlin. And my excitement was a little diminished at this point, so I'll make a formal complaint about it. In Kotlin, they gave a beautiful keyword called fun, because they want you to have fun every time you write code. But then they said, suspend fun. Come on. What is this? Anyways, so that's my formal complaint about it. It should have been a better name for it. But in this case, of course, I'm going to say suspend. But when I execute the code, what does it really do? So you can see in this case, the call is entering task 1 and entering task 2 at the same time. The code became concurrent, as you can see right there. And then it comes back to exit task 1 and exit task 2. But that little coloring, that little almost seamless, the code structure is exactly the same. Just like in the case of Java, the code structure is the same, except you have a little visual cue of stream. And this is exactly my complaint about fibers as well. I love fibers, but I want the visual cue whether a code is safe to be called from a fiber. So if you can give me an almost seamless, I would love to have that. So I don't want a seamless code. The reason I don't want a seamless code is, as programmers, you and I know semantics matters. And if the visual cue can simply give me a little hint of the variation, I think we are really good with it. And that is exactly what I want in languages. So how can we prepare for the future? And the answer is actually extremely simple. I showed you quite a number of features here in different languages, in JavaScript, Kotlin, and maybe we can look at other languages. But I love these languages for two reasons. One is curious. Oh my God, look at all these features. They're fun to learn. But there's another reason I like to learn from these languages. And this reminds me of something I heard, which was absolutely mind-blowing for me. The schools in Chicago did a research study. What they did was they took very small children. They took children who were toddlers to a little bit more, and then they did an interesting study with these children. What they did is they took two groups of children. One group of children were children who were exposed to only one language. Why use the word expose? And the reason is these were children whose parents spoke one language, their school spoke one language, their friends spoke one language, their nanny spoke one language. They were exposed to only one language all the time. The second group of children they were working with where their parents were speaking still one language, but their nanny was speaking a different language. Or they had children in school who spoke a different language. And what they did was something really, a research where they had the children in front of them, and they had objects all over the room. Imagine for a minute that I have an apple, fruit sitting here, and I have an apple sitting in front of me. And they would go to the child who was exposed to only one language, and they would ask the question, how many fruits do you see? And the child would say 2, because there was one fruit here in front of me, between the child and the person who's asking the question, and one behind, and the child would say 2. But then they would go ask the same exact question to the child who was exposed to multiple languages. And surprisingly, consistently they saw this. The children who were exposed to multiple languages, when they are asked the question, how many fruits do you see? They would look around the room and they would say 1 and not 2. Because these children were processing and saying, wait, the person is asking the question, it's obvious the person doesn't see what's behind the person, and they would remove what the other person won't see. And these were children. And how could children do such processing where, and their analysis is, when children are exposed to multiple languages, they are thinking in terms of other people rather than thinking in terms of themselves. And so they were removing objects the other person could not see. And this is very intriguing. And I'm definitely not a expert on these ideas, but I can vouch for it from the programming languages point of view that I've actually seen quite a bit. When I used to program in exactly one language all the time, versus when I started programming in multiple languages, it was like a mind blown, because I started seeing things differently, not in those other languages, but in the language I was programming in. I'm going to say the amount of time we need to learn a new concept is inversely proportional to the number of diverse ideas we have been exposed to. So if we want to accelerate learning and adapting to change in one language like Java, one of the best ways to get ready for the future of Java is to explore other languages on the JVM today. And that is one of the best ways we can be ready for the changes in Java. And I can prove this to you already, because when Java 8 came out, there were two kinds of programmers I worked with. Those who had programmed in other languages, and they said, how is Java's lambdas different? And programmers who never bothered to look at any other language, and there was a very steep learning curve for them getting to lambda expressions because it was a very alien concept. In fact, they were resisting the change more than even accepting it, because it's really hard to accept it when you have not been exposed to it. So learn different languages, not to use them all, but I want to learn different languages to adapt the changes quickly and easily as the language I program in predominantly begins to evolve. And Java is one language that is evolving very rapidly moving forward in a very pragmatic, in a very sensible way, in my opinion. But the best way to prepare for the future of Java is to really explore other languages today. And not because I want to go program in those languages, but I can come back and learn Java in a better way and be ready for it, be prepared for it. And the fact that I've really got exposed to things like continuations in Kotlin and other languages, I am eager to see what's happening in Java in terms of continuations and fibers, and I can relate to that much more easily because I've been exposed to these in other languages, and I think that is a lot more fun. So don't wait for the future, I would say, because the future is already here, and it's just a question of us adapting to it. Thanks for the time.